Here is the next example of MOSFET. Here we are doing AC analysis in this example. So based on the basic knowledge we have or gained from the DC analysis, we know that as long as the arrow is going out, that is N channel MOSFET, and the arrow is always on the source side and gate and drain. Okay, and we know that there won't be any current passing through the gate because this is always insulated. I mean, there is an insulation between these two plates. Now we are doing AC analysis. To do the AC analysis, we have to do the basic DC analysis. The given data, Kn prime times width over length is given and Vt is given. Okay, so based on this, first we'll do the DC analysis. So while doing DC analysis, we know that capacitor act like a open in DC, so I'm going to eliminate this. At this point we are doing only DC and eliminate this because capacitor act like a open in DC, and that's RL, load resistance 4 kilo ohm connected there. Now there are two modes of operation. One is saturation mode, another one is triode mode. So we always assume the saturation mode, start solving. If it is not satisfied the requirement, then we'll try it in triode mode. If you have more questions, please watch my previous video. Now in saturation mode, ID is, this is the formula for saturation mode, ID equal to half Kn prime width over length times VGS minus VT whole square. VT is given, VGS is nothing but VG minus VS. So VG, since there is no current passing through this 50 kilo ohms, IG equal to 0. So whatever the voltage here, 2 volts is going to appear there. Okay, so 2 minus VS. VS I can write it down as here, this is grounded. So VS minus 0 must be 4K times ID. So VS equal to, I'm going to write it as 4K times ID. If I take ID in milliamperes, that's 4 ID. Here also I'm going to take ID milliamperes because Kn prime is given in milli. Okay, so if I take that in milli, so here is the quadratic equation. We end up with 6.4 ID square minus 4.2 ID plus 0.4 equal to 0. Then I end up with, it's a quadratic equation, I end up with two values, ID equal to 0.541 milliampere, ID equal to 0.115 milliampere. So I'm going to solve for 0.541. So if I take 0.541 Vs, the voltage across this 4 kilo ohm, we found that as 2.164. Actually I do not care about the voltage across this 4 kilo ohm. All I care for the voltage right there. Same thing, I'm going to care for Vd right there. So 4 minus Vd equal to 4K times ID. Remember, the current passing through this and this is same because the gate current is 0. So I found Vs and Vd. I found Vds is a negative number. So basically here is a transistor. You have, that's a Vd 2.16, sorry, that's 1.8. Vd is 1.836 and Vs is 2.16, and you're saying current is passing down. Is it possible? No. Current always flows from higher potential to lower potential. Here it is going in the opposite direction. So this is not the right current. So we're going to take ID equal to 0.155. This is where I solved. I solved for Vs equal to minus 0.46, Vd equal to 3.4. So here I have 3.4, here I have minus 0.46 for sure, and current can pass through that. Okay, and I found that VGD is less than VT, so this transistor is working in saturation mode. That's how we'll verify. Now once we're done with that, we're going to do AC analysis. So while doing AC analysis, there are two ways. One is you can do the pi model similar to the BJT or T model. So we will use pi model as long as the source terminal is grounded while doing AC analysis. We can do the T model too. If you can solve an example by using pi model, for sure you can solve it by using T model, but the pi model is easy to do the calculation. So that's the reason, if it is possible, we will use the pi model. In this example, my source is not grounded while doing AC analysis, so we have to do the T model. So here is the AC analysis circuit, equivalent circuit. The resistance here is R0. R0 is resistance between the drain and source. Here is my source, that's my drain, and here is my gate. Okay, remember there won't be any current passing through that. And these are my input terminals where we are connecting input. That's what our input terminals are, and that's our input resistance. So there are few parameters. That's GM, transconductance, that's the formula you need to remember, and R0 equal to VA over ID. ID we found in DC analysis. Sometimes instead of VA they will give you 1 over lambda. In this example he gave us VA equal to 100 volt. That's given by the manufacturer. So my R0 equal to VA over ID. So here we just found ID equal to how much? We just found 0.115 milliampere. So R0 equal to 100 divided by 0.115 milli. So that value is 869 kilo ohms. That's a very, very big number. Okay, probably we can ignore that, because when we consider these two in parallel, 869 parallel with 4K, that's a 4K. So R0 is since very big number, close to the infinite. Anyway, we'll leave it there. It might be useful to find output resistance now. And the GM is nothing but transconductance. We know Kn prime times width over length. That value is given by the manufacturer. That value is 0.8 milliampere per volt square. So here R0 equal to 869 kilo ohm, and GM transconductance square root of 2 times Kn prime times width over length times ID. So we'll end up with 0.428 milli. It's not amperes. Transconductance is in Simon, so which is inverse to the resistance. So when it comes to 1 over GM, which is 1 over 0.428 milli, that will become 2331 ohm, or 2.33 kilo ohm. Now, okay, that's what we know. Now we'll find the input resistance. Remember, there is no current passing through the gate right there, so I can ignore the rest of the circuit while finding the input resistance. So my input resistance from the given circuit is just 50 kilo ohm. Okay, whatever connected between the input terminals. These are the input terminals, this terminal and ground. My output resistance similarly, okay, when we look at the output resistance right there, whatever the current passing through this, so the current here, it must be GM times VGS. Okay, since there is a dependent source, I should have connected a test current. So while finding R out here, you need to connect either test voltage or test current source because of the dependent source. So when I connect that 1 volt current source, 1 volt voltage source, the current is going to come here and pass through this because my VGS is 0. Why VGS 0? This VGS is the voltage connected on this, on the gate side. Okay, if I do not have any voltage there, the voltage there is going to be 0. So my VGS is 0. So in that case, there won't be any current passing through it. My output resistance is same as the resistance between the source and drain. So here that value is a big number, like 869 kilo ohm. Okay, so I found the output resistance, I found the input resistance. Now our goal is finding the gain. Okay, for gain with load, gain with no load, first we'll find AV, gain with load. So when I find the gain with load, so all I need relation between this and input voltage, okay, V0 and V input. So AV is the gain, which is V out over Vn with load resistance with RL. Now when we look at this circuit, we'll try to find an equation. I can see these two are in parallel, RL parallel with R0, and the current passing through this must be GM times VGS. Okay, so I mean, you can see it here. If I have RL there, I mean, these two resistors are in parallel, and my goal is finding V0 when there is an input is connected here. Okay, since input is there, there should be VGS. Okay, so now these two are in parallel. I can say my V0 equal to minus GM times VGS times R0 parallel with RL. My R0 is very big number, 869 kilo ohm. RL is only 4 kilo ohm. So if you combine 869 parallel with 4, approximately equal to 4 kilo ohm. So for time being, I'm going to take that as 4 kilo ohm. So V0 equal to minus GM times VGS 4K. Okay. Now VGS, when we looked from the input side, this is the voltage across this. So my V input is same as, can I take that as this resistance is 1 over GM. VGS. My VGS equal to total times 1 over GM by 1 over GM plus RE. We know 1 over GM is like 2.33 kilo ohms. RE is 4 kilo ohms. So the voltage here is Vn. I'm trying to find VGS. So VGS is nothing but Vn times the same resistance, 2.33 kilo over 2.33k plus 4k. So here I end up with VGS equal to 0.368 Vn. So I'm going to substitute that right here. So V0 equal to, V output equal to minus GM. So we know what is GM, 2.33k. VGS is 0.368 Vn, and then 4k. I'm sorry, this is not 2.33k. GM is 1 over that value. We just found GM value. It's little over midnight, so kind of 0.428 milli. So I have to use 0.428 milli here. Okay, this is 0.428 milli. So milli and kilo get cancelled out. So we'll end up with V0 over Vn equal to minus 0.63. So the gain is negative here. At the same time, it's less than 1 volt per volt. This is the gain. Now, when it comes to the no load gain, V0 over Vn, which is AV0. AV0 is without any load. So when I consider no load, this RL is going to disappear. So this is a very big number, like 863 something, 869. Okay, so if I have that number, then this is going to be negative 0.428, 0.368, and 680. I'm sorry, got that number again. Sorry, 869. So if you combine these 3, we'll end up with AV naught. Okay, combine means not addition. We need to multiply here. So we'll end up with 136.87 volt per volt. So my load resistance changed my gain a lot. So instead of using 4 kilo ohm, if I use the bigger number, more and more resistance at the load, then my gain is going to be more. Okay, now overall gain GV is nothing but overall gain AV times R input over Rn plus R sig. Okay, so AV I have minus 0.63. Okay, input resistance we just found, that is 20 kilo ohm, sorry 50 kilo ohm. Input resistance I just did here, there you go. Here is the input resistance, 50 kilo ohm. Okay, that's 50k over 50k plus 20k. R signal is 20k. So based on this, you can find the overall gain. So my overall gain is minus 0.45 volt per volt. So if I give 1 volt, I'm getting out only 0.45, and that is going to be inverted. It is not upright signal. So that indicates that if I draw waveforms, here is my input waveform, V input. Okay, and this is the time, or omega t. Say this value is 100 sine omega t, or 100 millivolt, sorry. I'm going to take that as 100 millivolt. That's the given value. That's given by the, definitely I'll mention that in the question. If not, just take it as 100 millivolt. Okay, here is my omega t, and my output V naught is going to be, overall gain with overall gain, it's only minus 0.45. So it's going to be only 45 millivolts, but that's going to be in the opposite side. So that is 100 times 0.45, that's 45 millivolt. Okay, I have 100 millivolt and 45 millivolt. Now sometimes we need to include the drain voltage. What we have the drain voltage here, VD I have 3.459. so if we include the drain voltage 3.459, because it is connected, my output is connected to the drain, right? So 3.459, so it's going to be something like this. So this is 3, this must be 3.45 plus 0.45, .45 plus, if I convert that into volt, it is 0.045, very less. So this must be 3.45, the lower limit. This must be 3.45 minus 0.045. Okay, that's the lower limit with the DC voltage included. Okay, I'll stop this video here. So as mentioned, you can solve any example by using T model. But if while doing AC analysis, if the source is grounded, then you can use the pi model. Pi model is easy to solve. So if AC is grounded, use the pi model. Okay, I will stop it here. Next example, I'll try to solve a pi model. Thank you.